last unit, our last topic that we'll be dealing with is work, energy, and power. And essentially, these last two units, momentum and work, energy, and power, we're moving away from just analyzing motion very specifically in terms of velocity and acceleration. We're moving into these quantities that are conserved. We have the law of conservation of momentum. We also have this other law called the law of conservation of energy. And both of those laws together can allow us to solve problems that previously were more complicated, and it should somewhat simplify them a little bit now. So let's start off with this concept of work. Okay, you get assigned a whole bunch of work at school. We make you do work. You make me do work. Sometimes you get paid for doing work. Sometimes you don't get paid for doing work. So what the heck is it? What is this idea that we talk about as being work? Those are all reasonable definitions of work, and it is a term that we use all the time. In physics, we'll talk about it a little bit more specifically, but the idea behind work is that when you do work, you transfer energy. Okay? Energy is being transferred either from one place to another or from one object to another when work is done. So work and energy are these interchangeable concepts, okay? Someone talked about force and time and things like that. It turns out that in order to do work in the physical sense, you must exert a force in the direction of motion. You must exert a force through a displacement in order to have work be done. So I can sit here and push against this wall forever. And if that wall does not move, I have done no work. I have done no work. If I lift up some barbells, like, you know, those like Olympic lifter guys, mathematically, if we want to look at it very simply, this is it. Work equals force times the displacement through which that force was exerted. Now notice this is very, very similar to impulse. Impulse was a force times the time that that force was being applied, and that caused a change in momentum. In this case, if we take a force and exert it through a certain distance or displacement, we will have done work and have transferred energy. What's the unit for force? Newtons. And the unit for displacement? Meters. So notice that work is this unit that is a Newton times a meter. A Newton of force exerted through a meter of distance does a certain amount of work, and we give that unit, instead of calling it Newton meters, we're going to call it a joule, named after James Prescott Joule, who was the physicist who discovered the law of conservation of energy. Okay, so again, the critical thing to remember with work, you guys, is that the force has to be in the direction that the displacement is happening. So let's look at this example for a second. You're backpacking. It's hard because you got this big old heavy thing on your back, and you're doing work on that backpack by transporting it from one place to another. What direction is the backpack exerting a force on you? Downward, because that's the weight of the backpack. So technically, you only do work on the backpack when you move it vertically. All the horizontal hiking in the world, you're not actually doing work on the backpack. You're doing a little bit of work to overcome friction and things like that, but you're really not transferring any energy to that backpack. Only if you're going up. If you're going down, the backpack's doing work on you at that point. It's exerting a force downward on you. So notice that, let's say I go a distance here, you know, we go a certain distance, and this backpack has a certain amount of weight. If I want to figure out how much work I've done on the backpack, what I really need to know is how much vertical distance I've lifted it. And if I take that vertical distance times the weight, because that's how much force I have to exert to move it with a nice constant velocity, that will tell me how much work I've done on the backpack. Okay? Does that kind of make sense?
Is that why it's easier to push?
Cool. Let's try it. See what we can do. We'll practice. Give it a try. You got 12 and a half seconds. So be careful with this one, because 10 kilograms is the mass, not the weight of the object. So you need to figure out the weight of the object to figure out the force it takes to lift it. In this case, 10 times 9.8, or sometimes 10 times 10, depending on how you're doing it. And then you take that times 0.8, and that gives you the answer of 78 joules. A Newton meter is a joule. Yep. Okay. Let's try another one. Forklift raises a box, does some work. Please tell me what the mass of that box was. I got 595. Okay. So yeah, if you take the work divided by the distance, that will tell you the force, which in this case would be the weight of the box. That's not the mass. You take that weight, divide it by 9.8 or 10, and that'll give you the mass. 595 kilograms. Okay? That's a comma. Exactly. Okay? Excellent. Now, sometimes we have situations where we're exerting a force and it's not constant. It's a changing force. And that gets a little bit trickier, but when we have graphs, it's super, super easy. And one of the things you need to recognize is that if I have a graph of force versus distance, the area under that graph is equal to the work. Area under that graph is equal to the work. Okay, here's a graph of force versus distance. And in the simplest terms, if I exert a constant force through a certain distance, right, and I calculate the area under this line for that distance, okay, that's the work done. Awesome. But if I have a situation where the force is not constant, okay, here's my force, here's my displacement, and instead I exert a non-constant force. Whoa. As my displacement goes, I'm exerting more force. Even though I don't have a square anymore, the same holds true. If I calculate the area underneath this line, in this case that triangle, that would tell me the work done. You with me? Good? Okay. This was similar to momentum, but in momentum, we would have a force versus time graph. Okay? And this would give you impulse, right? This would give you impulse, which is equal to the change in momentum. All right? So they're very, very similar. If you have a really complex situation, let's say you have a situation where the force of an object increases with the square of the distance. Okay, this gets more complicated. You won't really need to do this in this class, but I just want you to be aware of it, that there is a tool that you can use to find the area underneath this function. And that tool is called integral calculus. It is one of the major things in calculus where you integrate a function. And by integrating it, you actually find the area under the curve of that function. So if I just took the integral of an f versus d function, it would tell me the work no matter what it is. In this class, you won't have to do that, but if you ever start studying calculus, you can see how that applies. But you should recognize that if you have a force versus distance graph, the area underneath will be the work. Now, one situation that does act just like this, where the force increases linear with the distance, is a spring. When you stretch a spring, the more it stretches, the harder it pulls back. Okay? This is known as Hooke's law. There's a whole law related to it. And the force that a spring exerts is equal to some constant times its displacement, how far it's stretched. That's why it's that nice linear graph. If I want to figure out the work done on a spring, think about this. If I stretch a spring, I've done work. Work is a transfer of energy. Where does that energy go? To the spring. That spring is storing energy. And if I want to figure out how much energy it stores, I calculate the area under this curve. How do you find the area of a triangle? 1/2 base times height, right? And in this case, that's going to be 1/2 displacement times force, right? But force for a spring is just this constant, whatever the spring, that tells me how stiff the spring is, times its displacement. So I end up with this equation that says 1/2 k, which is a constant, s squared. We'll talk about this a little bit later in the presentation, but remember that. This tells me how much energy is stored in a spring, and it came from finding the area of this triangle. Okay? So here's what we just talked about. Here's a non-constant force. Here's a force versus distance graph. Again, it's non-constant. In this case, it's even kind of curvy. If I could find the area under this curve, I could figure out how much work was done in that distance. And for us, generally, that'll be basic geometry. But if I had calculus, I could also take the integral. Now, another situation that comes up in life is that we don't always apply a force in the direction of motion. Sometimes we apply a force in one direction, and motion happens in a different direction. And the critical thing is that work is only done by the force, the magnitude of the force in the direction of motion. So previously I said work equals force times displacement, but a more general definition, and I think this is actually what's in your data booklet, is that work is equal to Fs times the cosine of the angle. And that angle is the angle between the direction you apply the force and the direction the object moves. Okay? So Miles, this is kind of what I was talking about a little bit. So here's a woman who's trying to slide this heavy crate across the floor. She can't lift it up. It's too heavy. So she attaches a rope to it, and she pulls it and drags it across the floor. Notice that the force that she's applying is not in the direction of motion. So in order to figure out how much work she did, what we really need to find out is the force that she applied in the direction that the box moved. And that's where that cosine comes in. We take a vector, we break it down into its components. We figure out the force in the direction of motion times the distance it moves that direction. That tells us how much work she did. Okay? The work in this case is horizontal. What is she actually working against? Friction. In this case, she's not doing work on the crate. She's doing work against friction, right? The crate's not gaining any energy. It's basically just moving across the floor. And the reason she has to do work is because there's friction. If there were no friction, how much work would it take to move it? Zero. I mean, you have to push it to get it going, but once you got it going, infinite amount of work would happen. It would just keep on going, right? Actually, no work would happen, but it would move. It would move without work happening, I guess is what I mean. So here's the same situation. Let's actually plug in a few numbers and see if we can figure this out. Let's say that she pulls with 264 newtons of force. Is that practical? Sure, she's pretty strong. Please tell me how much work she does moving that crate 40 meters across the floor, and she's pulling at 37 degrees above the horizontal. So tell me what you get when you do this calculation now. 8,430. Okay, and what would our units be? Joules. Okay. Do you understand why that cosine is in this equation now? Does that make sense? Please be careful, because IB wants you to understand that and not blindly remember the equation, because sometimes what IB will do on a question is maybe give you this angle. You with me? In which case it would no longer be cosine. It would be sine. What you need to know that you're doing is trying to find the component of the force in the direction of motion. That's more general and a deeper understanding of what that equation is telling you. Okay? That's our basic definition of energy. It is the ability to do work. You can think of them as being interchangeable quantities. Energy is kind of like stored work. Work is transferring energy. They are interchangeable. If you do work on an object, you give it energy. If an object does work, it loses energy by the same amount. And the first type of energy I want to talk about is potential energy. E sub P. Some books give this the letter U, but I believe IB uses E sub P. Potential energy. Potential energy is the energy that an object has by virtue of where it is located. Specifically by where it is located in a gravitational field, if we're talking about gravitational potential energy, but there's also electrical potential energy. And it's the energy that something has by virtue of where it's located in that electrical field, okay? When we're talking about gravitational potential energy, the most simple way to calculate it is simply by taking the mass times the acceleration of gravity, which is the same thing as the gravitational field strength, times the height that it has been lifted. That tells you how much potential energy something has. There's another kind of potential energy that we talked about just a little while ago with springs and things like that. And the potential energy stored in a spring is equal to 1/2 k s squared. S being displacement, or how far the spring was stretched, and k being this thing called the spring constant that just basically tells you it's a constant for each spring. A stiffer spring has a bigger spring constant. So those are two basic kinds of potential energy. If I lift something up, I've given it potential energy. If I stretch a spring, I've done work, I've given it potential energy as well. Okay? Work and energy being interchanged. Here's a brick. Give me a number. 4. This brick weighs 4 newtons. Okay? And I lift it 2 meters. How much work do I do in lifting that brick 2 meters? Okay? Lifting it from here to here, I have done 8 joules of work. And now notice that my brick is located up here. How much potential energy does it have? 8 joules. And you could know that because that's how much work I did on it. Or you could do the equation we just said, mgh. mg is how much it weighs, and h is how high it is above wherever I'm going to drop it to, and that tells me that it has 8 joules of potential energy. Now here's the other thing. Let's say I did 8 joules of work. It now has 8 joules of energy. What happens if I drop that brick? When I drop it, what will that brick actually physically do? Fall. And will it still have the same amount of potential energy? No, that potential energy is disappearing. But I told you at the beginning that there's this thing called the law of conservation of energy. Energy can't be destroyed. So where is that potential energy going? Okay. It's going into its velocity. Velocity is going to be another type of energy we'll talk about in a second. And then when it hits the ground, what does it do? Makes sound. It does some work, right? It exerts a force through a distance. It does some work. So again, energy and work constantly being interchangeable. So I do 8 joules of work on it. Some hapless little squirrel is running underneath, and I drop it. That potential energy turns into kinetic energy. Then it does work on the squirrel by hitting it. Bad news. Okay, so but just remember that it's always interchangeable, this work and energy. So here comes our second main type of energy, which is called kinetic energy. Kinetic energy is the energy that something possesses by virtue of its motion. Remember, potential energy is the energy by virtue of something's location. And basically, if an object is in motion, it has an ability to do work. I want to show you something here real quick. We talked about Newton's second law for a long time, right? And therefore, the acceleration of an object equals force over mass. We also know from kinematics way back when that the final velocity squared equals the initial velocity squared plus 2as, right? And so I can say that if something is starting from rest, the final velocity squared equals 2 times F over m times s. With me so far? Just substituting F over m for a, okay? And then what I can do is I'm going to rearrange this a little bit, and I'm going to go 1/2 mv squared equals force times displacement. Does that make sense so far? And what did we just say force times displacement was? Work. And what did we say work does? Energy. So this work must be giving us some kind of energy. And this is an energy that deals with velocity or motion, so it turns out that 1/2 mv squared is kinetic energy. The energy that something has by virtue of its motion, what we call kinetic energy, we can calculate now by taking 1/2 the mass times the velocity of the object squared is equal to the kinetic energy of the object. What's the unit for kinetic energy? Joules. What's the unit for potential energy? What's the unit for work? They are interchangeable, okay? They are interchangeable. I think your book also says this, that kinetic energy is momentum squared over 2 times the mass. If you guys want to try to derive that equation, you can. I think if you just use the kinetic energy equation and the momentum, P equals mv, you should be able to get to that second equation. Try this problem. Rifle shooting a gun. We've talked about rifles and guns in terms of momentum, and that's one way to solve these problems. But now let's talk about them in terms of energy. So for this first one, we just use 1/2 mv squared, making sure that we're measuring our mass in kilograms, right? What would be the answer for the second one? Gardner, why do you say that it's the same as the first one? Work is energy. How much kinetic energy did the bullet start with? 0. How much did it end with? 1956. So that's its change in energy. That means that's how much work was done on it, right? Work causes a change in energy. So this answer is the same as this answer.
Change in energy work.
Yes. Yep. And therefore, if I know how much work is done, can I figure out how much force is applied to the bullet?
Yes.
Because work equals force times distance. We're assuming the force is in the direction of motion of the bullet. The force is pushing it out of the barrel. And what do you get for force then when you do that?
14, 1,470 joules.
So there we go. Work equals force times distance. We can then figure out how much force was applied. Okay, I want to review one thing real quick. We talked about, with momentum, we talked about collisions. Do you guys remember the two different types of collisions? Elastic and sticky, also known as inelastic. Great. Is momentum conserved in an elastic collision? Yes. Is momentum conserved in an inelastic collision? Yes. So momentum is always conserved. The difference between elastic and inelastic is in a perfectly elastic collision, the kinetic energy, what we just talked about, the total kinetic energy of the objects will be conserved before the collision and after the collision. That makes it elastic. An inelastic collision is where the kinetic energy is not conserved. But we talked about this law of conservation of energy. So if the kinetic energy is not conserved, what happens to it? It can't just disappear. It goes into other forms of energy, friction, sound, heat, potential energy of crumpled metal, stuff like that. So, excellent. Finally, let's talk about power, because I know that I'm overwhelming you guys, and this is it. This is the last thing. Power. Okay? Power is the rate that work gets done, or the rate at which energy is consumed or transferred. Okay? So basically, mathematically, it's pretty darn simple. Power is just work divided by time. Work divided by time. Now, since we could do some rearranging here to show you that we could also come up with another equation for power, because what does work equal? Force times distance?
Yes.
And what does distance over time equal? Close. Velocity. So another way to calculate power is force times velocity. All right, and those are both in your equation packet, I believe. We have a new unit. We have a new unit to measure power in, and it's a unit that you're familiar with. What do we measure work? What do we measure work in? Joules. And what do we measure time in? Seconds. So there must be a unit that's equal to a joule per second. A joule per second, and it is something that you just mentioned, Cole. It's called a watt. It's called a watt. And you're probably familiar with watts because we measure light bulbs in watts. You know, you have a 100-watt light bulb. Well, what that's telling you is that in order to make light, that 100-watt bulb has to use 100 joules of energy every second to make that light. It makes a lot of heat as well, depending on what kind of light bulb you're using. Give this one a shot. Remember, power is work divided by time. So let's figure out how much power this elevator or electric motor uses. So if I just calculate the work and I divide it by the time, I figure out how much power was consumed or generated. Okay? 7,200 watts or 7.2 kilowatts. Now notice that most electrical appliances, almost anything that you plug into a wall, if you look somewhere on that appliance, usually on the back or on the bottom, there'll be a little plaque, and it'll tell you the power rating of that appliance, how much power it consumes to run. And it's sometimes remarkable. Sometimes it's not, but you know, take a look at it. Some of them are very small power, some of them are big. Your microwave, your refrigerator, anything you plug in, computers, all that stuff. They didn't say retarded forces. They said the retarding forces. Not what? Okay. You like that? No, it's not. So there's a lot of steps to that one, but it's not totally unbearable. It sounds like that it might have been hard, but there you go. So here's a review, because we've thrown a lot of equations at you. Hi, guys. Work equals force times distance, right? But really, work equals force times distance times the cosine of theta. What else? Potential energy is mgh. Kinetic energy. Oh, elastic potential energy is 1/2 ks squared. Kinetic energy is 1/2 mv squared, and also momentum squared over 2m. And finally, power equals work over time, or power equals force times velocity. Lots of equations, but none of them in and of themselves are that challenging of equations. Pretty straightforward stuff.